Hello. If you ever thought of preparing for a coding interview, you probably heard of dynamic programming as one of the common topics. In short, dynamic programming is a process of solving a problem through its iterative simplification, as opposed to specifying a robustly defined series of algorithmic steps. Sounds a bit like machine learning, right? But is it actually that complex? The most common dynamic programming approach is recursion, having a function call itself. Again, this sounds like it would rather hang the program before doing something of value. But let's see how it can actually work. Okay, so consider a following example. Find a prime decomposition of a positive integer n as a list of its prime divisors with respect to their multiplicity. So, for example, for n equals 12, the decomposition we're looking for is 2, 2, 3. Sounds like a somewhat complex approach might be needed here. At least we're unlikely to manage it within a single loop. Or can we? Okay, let's implement a function to return prime decomposition of n as a list of its prime divisors. So first, implement a loop to find the first divisor. We'll search trying the numbers starting from 2. But when to stop? Do we actually need to go all the way until n? Obviously, no divisor can be larger than n. In fact, if p is a divisor, then n divided by p is another divisor. And at least one of those can be greater than square root of n. So it's actually enough to search the numbers from 2 to square root of n, which will save computational time dramatically. Okay, now if p is a divisor, let's check that. How can we find other divisors? Here starts the magic. We only find one divisor, but we can finalize the code right here. By returning p, in addition to the list of divisors of n divided by p, which is returned by a recursive call of the same function. Literally like that. So let me hold with the explanations of why would it work for a few seconds until we finalize the code here. The last thing we need to do is to account for the case if the function survived this entire loop and there's no other divisor found. In this case, n is the only divisor, and we finalize the function by returning n. So as simple as that, only 5 lines of code. Does it actually work? Let's try it first for a small number like n equals to 10. 2 by 5, correct. 100. 2 times 2, 2 times 5, correct. 120, correct. Something more complex, we can check that it actually works correctly. Exactly. Now let me try a really large number, like 6, 7, 8, 9, 0. It still works pretty fast, and you can check that it actually works correctly. So why would it ever work? First, notice that a recursive call of prime decomposition has an argument n divided by p, which is always smaller than n. So the values of arguments keep declining while we go deeper and deeper in the recursion, and this way we can't go forever. At some point, we'll reach the number n, which doesn't have any further prime divisors, and we'll start returning the values that way. And if you're wondering why the divisors are prime, that's because before finding any non-prime divisor p of n, the loop will eventually find a smaller prime divisor and won't go any further. So we saw how a problem which initially appeared as somewhat complex turned out to be solvable within just 5 lines of code, and a simple for loop with a recursive call within it. Actually, every time we see a complex problem which is difficult to solve right away, a good thing to consider is if we can actually solve it, if we know the solution for a somewhat smaller setup. Like here, if we know a solution for n divided by p, can we solve the problem for n? If so, recursion may be a way to go. Hope you'll find it helpful, and please stay tuned for other topics to discuss.